Every train wheel on Earth is shaped wrong, not by accident, but by design. In 1827, engineers deliberately built a subtle cone into the tread, a taper so counterintuitive it looks like a manufacturing defect. That shape allows 1,000-ton trains to steer themselves without a single motor or electronic signal. But here's the twist. The same geometry that keeps trains on the rails also tries to throw them off. A violent wobble that has derailed high-speed trains and cost nations billions to fight. And the reason we cannot simply fix it is perhaps the most bizarre part of all. In the smoky workshops of northern England during the 1820s, the future of rail travel was being hammered out, sometimes literally, by men like John Birkinshaw and George Stephenson. Birkinshaw's work at the Bedlington Iron Works had already made his name by inventing a malleable iron rail tough enough for the pounding of early locomotives. But the rails themselves were only half the equation. The real puzzle was the wheel. Early attempts used nearly cylindrical wheels, but the results were rough riding and relentless wear. The rails groaned under the stress, and the flanges, those raised edges meant to keep wheels from slipping off, wore down far too quickly. Birkinshaw's workshop notes from 1820 mention experiments with wheel shapes, searching for a profile that would ride more smoothly and last longer. By 1827, the mystery had deepened. Why did some wheels seem to steer themselves, while others fought every curve? The answer began to take shape in the margins of George Stephenson's engineering notebook. There, among sketches and calculations, Stephenson drew a wheel whose rim was thicker on the outside edge than the inside. A subtle, almost invisible cone. The drawing was dated 1827, and in a few lines of cramped handwriting he recorded that this new form, conical, to reduce flange wear, had shown promise on the Stockton and Darlington line. In a letter from April 1829 sent by the chief engineer of the Birmingham and Liverpool Railway to Birkinshaw's team, the engineer wrote that the larger diameter on the outer side of the wheel will naturally guide the axle towards the center of the curve, reducing flange wear. It was an insight born from trial and error, but it hinted at a deeper physics, a wheel that could steer itself simply by how its surface met the rail. The idea pointed to self-steering as a practical effect of shape. James Stimpson's 1840 patent, reissued in the United States, captured the idea with legal precision. The patent described a wheel tread formed so that the effective rolling radius varies laterally, thereby providing self-steering. The patent plates show a cone, its largest diameter at the rim, its smallest at the hub. This was not an accidental quirk. It was a deliberate engineering choice, one that left behind a paper trail of sketches, letters, and patents, each echoing the same theme. The patent record made the concept official. Workshop logbooks from Robert Stephenson and Company in the 1830s record the shift from trial to standard. Wheels were now turned to a precise taper, 1 part in 64, or about 0.9 degrees. Measurements from an 1836 batch list a running surface that grows by 5 millimeters, from hub to rim. Trials on the York Line revealed something remarkable. After 200 miles, there was virtually no flange wear at all. The taper had proven its worth. The conical wheel, with its outward taper, became the quiet hero of early railway engineering. Not because it looked right, but because it solved a stubborn problem. The archival record, Birkinshaw's specification, Stephenson's notebook, Stimpson's patent, and the workshop logs tells a story of invention driven by necessity, not theory. Yet, as the next chapter would reveal, this elegant solution carried a hidden twist. A shape that seemed perfect for curves would one day challenge the very limits of speed. A train wheel set is a single piece of steel, 2 wheels locked to a solid axle, forced to spin together. But the secret to its uncanny ability to steer is not in the axle or the rails. It is in the subtle slope of each wheel's running surface. Instead of a flat cylinder, every wheel is gently tapered, forming a shallow cone. That tiny angle, just under 1 degree, is enough to turn a brute force machine into a self-guided vehicle. Picture a train rolling down a perfectly straight track. Both wheels touch the rail at the same distance from the axle, so each travels the same distance with every turn. The axle stays centered, flanges barely touching the rails. Tracks are never perfectly straight, and trains rarely run perfectly centered. When the wheel set drifts to one side, nudged by a gust of wind or a bump in the track, the contact patches on each wheel shift. Now, the wheel on the outside of the drift rides higher up the cone, where the diameter is slightly larger, while the inside wheel drops lower to a smaller diameter. Here is where the magic happens. The larger diameter wheel covers more ground with each revolution than the smaller one. But because both wheels are locked together, they must spin at the same rate. The only way for the train to keep moving without slipping is for the axle to yaw or turn gently back toward the center of the track. The geometry does the steering. No motors, no electronics, just steel and math. Each time the wheel set slides off center, the difference in rolling circumference nudges it back. The effect is automatic, continuous, and astonishingly reliable. Engineers call this phenomenon passive self-steering. It is not just a neat trick. It is the reason trains can glide through curves at speed with minimal flange contact and far less wear on both wheels and rails. In the early 1830s, trials on the York Line showed that conical wheels could run hundreds of miles with almost no flange erosion. A revelation for railway operators used to constant repairs. The contact patch, that tiny ellipse where steel meets steel, migrates up and down the cone as the axle shifts, always adjusting the effective rolling radius to keep the train on course. The numbers behind this are small, but powerful. A typical wheel might grow by just 5 millimeters from the hub to the rim, but that is enough to create a rolling radius difference of several millimeters when the axle shifts sideways. For a train rounding a curve, the outside wheel needs to travel farther than the inside, precisely what the conical profile delivers, without any active intervention. This is the bizarre truth at the heart of railway engineering. The wheel looks wrong because it is shaped to solve a problem most people never see. It is a solution so simple and elegant that it almost disappears into the background of every train ride. But as engineers would soon discover, this same geometry that keeps trains on track also plants the seed for a new kind of instability, a twist in the story that would haunt high-speed rail for generations. At first glance, the conical wheel profile seemed to be the perfect answer: self-steering, less wear, and a smoother ride. But as trains began to run faster, a strange and unsettling behavior crept in. Engineers noticed that above a certain speed, the very geometry that kept trains on track could turn against them. The wheel sets, locked together and shaped to steer themselves, would begin to sway from side to side, almost as if searching for the center, but never quite settling. This wasn't a gentle drift. It became a rapid, rhythmic oscillation, what engineers would come to call hunting. Hunting oscillation is a technical term, but the reality is hard to ignore. As speed increases, the self-centering effect of the conical profile starts to lag behind the inertia of the wheel set. Instead of snapping back to center, the wheels overshoot, crossing from one rail to the other in a repeating cycle. Each oscillation grows a little stronger, feeding off the train's momentum. The carriages begin to rock. Passengers feel a side-to-side shake, and the wheels themselves start to lose reliable contact with the rails. At low speeds, this motion is barely noticeable. But beyond a critical threshold, the oscillation can become violent, enough to threaten the stability of the entire train. The danger isn't theoretical. On January 30th, 2022, a limited express train near Sapporo, Japan, derailed while running slightly above its design speed on a rebuilt section of track. The official report from the Transport Safety Board left no doubt about the cause. Excessive hunting oscillation led to a sudden loss of contact between the wheel flanges and the rail, sending the leading cars off the track. Investigators traced the sequence frame by frame. First, a rising lateral sway, then a sharp spike in wheel set acceleration, and finally, derailment. No mechanical failure, no broken rail, just the physics of the conical wheel profile pushed past its limit. The term hunting had been around for decades, but the Sapporo incident gave it new urgency. The data showed that as the train approached 130 kilometers per hour, the natural frequency of the wheel set's side-to-side motion aligned with the speed of the train. The oscillation built up over just a few seconds, overwhelming the bogey's ability to damp it out. Passengers described a sudden lurch, a rattling vibration, and then the jolt of leaving the rails. Safety board engineers, poring over the event recorder data, found that the yaw angle of the wheel set had exceeded safe limits by a factor of 2. This wasn't just a matter of discomfort. Hunting oscillation sets a hard ceiling on how fast a conventional train can safely travel. Push past the critical speed, and the risk of derailment rises sharply. The Sapporo derailment forced operators and engineers to confront a paradox. The very wheel shape that keeps trains on track at low and medium speeds becomes a source of instability at high speed. The elegant solution had revealed a hidden cost, measured not just in worn steel, but in real danger to passengers and crews. In the aftermath, attention turned to engineering fixes, dampers, redesigned bogies, new wheel profiles, all aimed at taming the oscillation without sacrificing the self-steering effect. But the lesson was clear. Every solution in engineering carries its own shadow. The conical wheel, so clever in its simplicity, had drawn an invisible line in the sand for speed, comfort, and safety. The mystery deepened, and the search for answers moved from the workshop to the laboratory, and finally, to the scene of modern derailments. Across 3 continents, the hunt for stability became a race against physics and against national pride. In Japan, the aftermath of the 2022 Sapporo derailment set off a surge of late-night meetings at JR East's engineering headquarters. The solution was yaw dampers. These hydraulic devices, bolted between the axle box and the bogie frame, act like shock absorbers for sideways motion, soaking up the sway before it can build into a dangerous oscillation. The numbers were staggering. JR East spent 1.2 billion yen to retrofit its 3000 series Shinkansen fleet, rolling out the upgrade in less than half a year. Maintenance crews worked in shifts, swapping out hardware on tight schedules to keep trains running. The goal was not to redesign the wheel or the rail, but to tame the instability with a passive, mechanical fix, one that could be tuned to the measured conicity of each wheel set. In France, the approach leaned into high-tech ambition. During the 2007 TGVPOS World Speed Record Run, sensors on the leading bogies picked up the telltale signature of hunting as the train crept past 570 kilometers per hour. The standard Y236 bogie was on the edge of its limits. Instead of slowing down, SNCF engineers activated an experimental system, piezoelectric actuators fitted to each axle box. These devices could sense lateral acceleration and apply a micro brake to the axle, nudging the wheel set back toward center. The system ran in real time, guided by onboard diagnostics. The post-run logs, quietly filed in SNCF's archives, reveal a glimpse of the future. Active steering that responds to instability before it grows. The cost of the test program ran into the millions of euros, absorbed into the broader research budget. For SNCF, it was a bet on software and sensors, not just steel. Germany's answer was as methodical as it was expensive. Deutsche Bahn, facing persistent hunting on its ICE-3 high-speed trains, ordered a redesign of the wheel tread itself. Engineers at the Bombardier plant in Hennigsdorf reworked the profile, lowering the equivalent conicity from 0.025 to 0.018. This subtle change meant remanufacturing wheel sets across the entire fleet. The price tag was 850 million euros, documented in internal cost analyses submitted to the Ministry of Transport. The redesign did not just tweak a few parts, it altered the geometry of every new wheel, shifting the delicate balance between self-steering and stability. The process required new tooling, recalibrated inspection routines, and months of production line adjustments. Each nation's fix reveals a different philosophy. Japan doubled down on passive damping, targeting the symptoms with robust hardware. France chased the promise of active control, weaving electronics into the heart of the bogie. Germany reimagined the wheel itself, trusting geometry to hold the line against instability. Yet all three share a common thread: a refusal to abandon the steel wheel even as the costs soared and the technical challenges mounted. The conical profile, so simple and so elegant, became the anchor for billions in engineering effort. The world's railways were not ready to give up on the wheel that had carried them this far, but the price of staying on track, both literally and financially, kept climbing with every new solution. Imagine a train that never wobbles, never rocks from side to side, and glides so smoothly that the old problem of hunting oscillation simply disappears. That is not a fantasy. It is the daily reality of Maglev. In Shanghai, magnetic levitation trains have been running since 2004, floating above their guideway at up to 430 kilometers per hour. There are no wheels, no axles, and no steel-on-steel contact. Instead, powerful electromagnets lift the train a few centimeters into the air and hold it steady, locked in place by fields that adjust thousands of times per second. Without wheels, there is no conical profile, no rolling radius difference, and none of the side-to-side sway that haunts even the best steel wheel designs at high speed. The entire question of flange wear, self-steering, and hunting simply vanishes. The Shanghai Maglev's daily timetable is a testament to this. It accelerates from 0 to top speed in under 2 minutes, then cruises at 430 kilometers per hour with a ride that feels almost frictionless. No mechanical steering, no dampers, no compromise between stability and speed, just a clean, silent leap over the old limits of rail. For engineers, Maglev is the answer to a century-old puzzle. It sidesteps every trade-off that shaped the evolution of train wheels, delivering stability and speed without the baggage of the past. The result is as close as technology gets to a perfect solution, at least until the question of cost comes knocking. Across the world, steel wheels still rule the rails. The global network stretches more than 1.3 million kilometers. Enough track to circle the Earth 30 times. Every meter relies on the same principle: a conical wheel locked to its mate by a solid axle, steering itself without sensors or software. But here is the twist. The very feature that makes railways so reliable is also the anchor that holds them in place. Replacing this vast web with Maglev, the wheel-free marvel seen in Shanghai is not just a technical challenge. It is an economic wall. A 2018 feasibility study from Japan's Ministry of Land, Infrastructure and Transport put a hard number on the problem. To swap out every steel wheel for magnetic levitation, the world would need to spend at least 2.7 trillion US dollars. That is the combined GDP of France and the United Kingdom poured entirely into new guideways, power systems, and rolling stock, just to match what already exists. In the United States alone, the estimate runs to $900 billion for its share of the network. China faces a $500 billion bill. Even countries with smaller rail systems like Japan and much of Europe would each need hundreds of billions just to start over. Transport policy in the European Union now openly acknowledges this lock-in. The Future Rail White Paper, published in 2023, calls for a dual-track approach. Preserve and upgrade the steel wheel backbone while building selective maglev corridors for airport links and city shuttles. The logic is clear. No nation can afford to walk away from a network built over a century, no matter how elegant the alternative. The conical wheel stands as both savior and shackle, a lesson in what engineers call path dependency. When an early solution, brilliant in its day, becomes the reason the world cannot easily move on. Every time a train speeds across steel rails, it rides a compromise. An elegant fix, locked in by history, yet haunted by its unintended side effects. Path dependency means the world's railways remain bound to a solution that is 200 years old, even as better options exist. Sometimes, the shape of progress is set not by what is possible, but by what is already built. How many other systems still run on yesterday's logic?